Recording there. Okay, so today we're actually smashed two lessons together, guys. So we're going to look at Eulerian graphs and trails, and we're also going to look at Hamiltonian graphs. The reason why is at the moment the amount of content we've got to get through will leave us with one revision lesson, and I want to give you at least two. So we're combining these two lessons so that we can have enough time to revise in a bit more depth not next week, the week after. Okay, so Eulerian trails, guys. This is gonna let me. There we go. Imagine you are a park ranger or something. You got to visit campsites and the roads between them. You might need to travel along all of those roads to make sure that none of them are like falling apart or anything like that. So if that was you and you have to like visit each of these roads, do you want to be going up and down the same road multiple times? It's a bit of a waste of time. So ideally, you want to travel each road once. So if there is a graph where you can travel along every edge of that graph once and not repeat any edges, we call that an Eulerian trail. So Eulerian. Um, Remember, we also have Euler's formula, which is to do with planar graphs. So this is a separate thing to that. So if you can travel every edge exactly once, it's Eulerian. Do you think you'll be able to reuse vertices in that instance? Have I said anything about not reusing them? No. So you're allowed to use vertices as many times as you want, as long as you're not reusing an edge. So let's have a look here. Do you think you can start at A and visit every edge without reusing an edge? What's our gut feeling, yes or no?
Yes. Yes.
Gut feeling no, gut feeling yes. Oh, whoa, hold up. Let me get me highlighter out. So where do I go first? Every edge. Hell no. Nah, you got to use every edge. Well, let's try it. So let's try going from A to B. Where might I go next?
B to F.
B to F.
G back to B. B to C.
Or we can come back. We can swing around there later. B to C. C to D. We can do, yeah. There's more than one way to do this as well. D to E.
B to C. C to G. G to E. B to F. Back on.
Bush. So that one is um uh, Eulerian. There's a bunch of people away at the JCU thing, and then there's a few people that, because their friends are away, have decided not to come. What's happening in Airlie? Goodness. Yeah, cool. Um, so guys, you guys bring up a good point. Like, you can't really just look at a graph and tell straight away. So there's actually a trick that you can always tell whether a graph is going to be Eulerian or not. And the trick is basically if each of the vertices has an even degree, so the number of lines coming out of it is even, it will always be Eulerian. There's one other special case as well. But looking at that, let's just check. So I'll get my pen up. So can we see that we have a degree of 2 for A, 1, 2, 3, 4 for B, 1, 2, 3, 4 for C, 1, 2 for D, 1, 2, 3, 4 for E, 1, 2, 3, 4, 1, 2, 3, 4. You see that all of those are even. Eulerian. If it's all even, it's all Eulerian. Even Eulerian.
Also, if
Yeah. Yep. And there's one other special case, but we'll talk about that in a little bit, and that's called a semi-Eulerian. So, Eulerian graphs, guys. The degree of every vertex in the graph is even, then he could begin at every campsite. A closed trail that involves every edge of the graph can be called Eulerian. A graph that contains an Eulerian is called an Eulerian graph. So if you can visit everything, that's an Eulerian trail, and if it has an Eulerian trail, it's an Eulerian graph. There is one special case. There is one special case. If there are two odd vertices in the graph, So everything is even apart from two odd ones. We call that one semi-Eulerian. Um, in that case, you can visit every edge, but you don't end up back where you started.
One, one, couple of
Yeah. Yeah. Or it might be like three
yeah.
and three or something like that. But you basically what happens, you will always start and end at one of the odd vertices. But only if there's two will it work. So a graph where an open trail exists involves every edge is semi-Eulerian. Graph is semi-Eulerian if it contains vertices with even degrees. So guys, like I said, this will be the first thing that I want you to jot down for today. So this is Eulerian and semi-Eulerian. So Eulerian graphs contain an Eulerian trail, have all vertices with even degree, allow you to begin at any vertex and travel to every edge. Only once return to the starting vertex. So in that first example we did, guys, we started at A, but we could have started literally anywhere and would have been Eulerians. Semi-Eulerian has more conditions, though. Those are those. Once you got that down, guys, hand out a sheet now. I'll just get you to go through these ones and say whether they're Eulerian or and yeah, obviously down the bottom there it says both Eulerian and semi-Eulerian have to be connected. Obviously, if you graphs in two bits, you're not going to be able to get one actually. Um, so, Clayton, just for your benefit, today we're pushing two lessons together. Because of the sports calendar and everything, if we don't do this, we'll only get one revision lesson before the exam. So we're just trying to smash through this lesson and then the next lesson, and at the end we'll give you some time to work through them both. I've also got for everyone today. I'm going to give you a practice exam. There is stuff on it that we haven't learnt yet, but I just want you to have that so that as we learn the stuff, you can practice those problems. Yes.
So what's the actual day?
It is Monday, week 4. So
So that's not August, is it?
I'll have a look. So it's week 1 now, 2, 3, 4. It is the 31st of July. Guys, I'm just gonna.
And then, because for the next couple of weeks after that, I have to ask if you can email me a load of stuff.
Yeah.
I miss work Mondays.
Is that for your work experience stuff?
Wait. So week 5, I think this Thursday, Friday, and Monday. So I'll miss 3 maths lessons in a row. Then I'll be here Thursday, and then I'll miss the next Friday and Monday.
Yeah, righto. Um. So where is it? Here we go. This is what I'm going to show you guys. If you have a look up here, these are the topics that we have left to do, and our exam is on the uh, Monday, section 4. So we've looked at Euler's formula, we've looked at cycles, paths, and now we're doing Eulers and Hamiltonians together. So we'll do shortest path tomorrow. We're doing Eulerian trails and Hamiltonian graphs together. We'll do shortest path tomorrow, trees and scheduling on Monday, and we'll try and smash through. Scheduling is the hardest topic that we'll do. Just FYI.
You go back to the slides.
Yeah, just give me one sec. Is that? Yeah, there we go. Cool. Caitlin. Which one? So the difference between them, Eulerian, everything is even. You can start and end it, but where you start will be where you end. You see if I started here. With this one that I believe you could start at any single vertex and go. That's section 9, right? Um, use every action order, and you could do that for any action order. With lettering, this one here. So you're allowed to have two odd in the semi. So this is just neither.
Is there a name for
So it's neither. See, that one might be a different type of. So just worry about sort of area wrong. So yeah, so that one's all even, so you get to go. Yeah, because it's got all odd aside from. Sorry, it's got all even aside from two. Oh, well, I thought we were going to have a point. It turns out people from Abbott Point were coming here. So I just sat in all day. It's very impressive. Mm. Oh. So a really common exam question, guys, is it'll say something like, describe this graph as Eulerian, semi-Eulerian, or Hamiltonian. We'll look at Hamiltonian in a second. So being able to just straight away remember Eulerian or even, semi to uneven. Then show you how it's pretty. Yeah. Sorry. Yeah, just it's even. They're all even units. So it's not. Yeah, so you can no sort of theories. But I sort of told you that ahead of time.
How long did it enter?
90 minutes. And I think they're going to put you in with the methods kids as well.
I think they said they were on after us.
Well, maybe.
Like we were going to all go to the no.
Uh, I was talking to Miss Moore the other day, and she said we're going 3 and 4 on the Monday, and I think that what'll probably happen is we'll do a 90-minute block because it's 90 minutes. But for us, that'd end up basically going into lunchtime. So what we'll probably end up doing is either we'll start partway through period 3. Um, so give you like 20 minutes just to like do any last minute revising. Or we'll start at the beginning of period 3, go into lunchtime, and then in period 4, when you'd normally have mass, we'll give you some time to sit around and have some food or whatever. We'll have to figure that out.
It started at like halfway through. So something like go to like 11:24. Started 11:30.
It's quite difficult to get students to rock up halfway through lunchtime, unfortunately. I would prefer that as well, Clayton, but it just logistically it's quite difficult, fortunately.
Like then start like halfway through first. So you still got second. So make us come back and start learning next unit. Yes.
Well, this is the last unit, but there are still topics to learn up to the exam. Yeah. To be honest, I don't think I'd make you do maths. Realistically, I'd get there and listen to you like say that question was gammon. All right. Oh, wow, I really won't be.
So I'll get one lesson back and miss 3 lessons and have
Damn, that is hectic. Okay. Do we want to go through that sheet, guys? That first graph. Are the vertices all even, some odd, or what? So they're all even. So what type of graph is it? Eulerian. Graph B over on the right there, that goes up to H. What are our vertices? Even, odd, all even? Yep, so that's Eulerian. Graph C, what have we got? All odd. So is that Eulerian, semi-Eulerian? Neither. You're only allowed to have two odd vertices for a semi. D, what do we got? All even. Yep. So that one would be Eulerian. For E, what do we got? Two odd, so that's semi-Eulerian. So just remember, guys, semi-Eulerian, which are our odd vertices in this one? E and D? Yeah, E and D. But where do you have to start and finish when you're doing all the edges on this one? Yeah, D and E. So you start at one, finish at the other. And then last one, guys, F. What do we got for our vertices? Even, odd, mixture. Yeah, they're all even. So that one would be Eulerian wax again. Okay, guys. Let's have a look at Hamiltonian graphs now. So, yeah, we've got some Eulerian stuff in here as well. So we just did that worksheet. Yeah, we did that. We talked about that. There is some textbook stuff on Eulerian, but I think are we all feeling all right about this? Like, it's pretty basic, right? We're not going to worry about that. But just really quickly, don't need to write it down or anything, but can you tell me for those graphs, are they Eulerian, semi-Eulerian, or neither? So A, what do we reckon? Yeah, because there's two even, two odd, so that would be semi. B, the second one. 2, 4, 6. Yeah, that one would be Eulerian because they're all even. And then the last one there, either 1, 2, 3, 1, 1. Yeah, so that one has too many odd vertices to be either, so that's neither. Okay. Guys, we're going to talk about a big nerd called Hamilton. He was Irish in the 1800s. He invented this puzzle game where it looks like that. And basically, you have these pegs, and it's kind of the opposite of Eulerian. Instead of visiting every edge, you've got to visit every vertex. Do you reckon looking at that board game, is it possible to visit each edge once, each vertex once? Yeah.
Without going back on.
You can't use a vertex you've already used. So you don't need to use every edge, but you need to use every vertex. Yeah, there's multiple ways to do it as well. So basically any graph where you can visit every vertex is called, without reusing an edge or reusing a vertex, is called Hamiltonian. So Eulerian, visit every edge, but you can reuse vertices. Hamiltonian, visit every vertex, but you can't reuse edges or vertices. So this is the puzzle. Well, I've prepared it so you don't need to try on the paper. Can you guys have a go? See if you can solve it. So start somewhere. Doesn't matter where you start. See if you can visit every vertex without using an edge or a vertex.
What is so many?
Why do I have so many? Oh, just because there's more than one way to solve it, but there's dozens of ways you can solve it.
Question.
Yes.
Sorry. Going back.
Yeah, the last one doesn't really count. Yeah, so you visit all vertices exactly once except for the start and end. So you basically got to do a big loop of your graph. Um, there's actually like this seems a bit silly. This is a really important field of maths. You might have figured it out. You find a different way to go as well. I'll get you to do one extra way. You don't need to do more than two. I'll get you to find one more way to go. Where did we start?
We have to use a bridge.
You've got to make it to the start of the vertex, so it's got to be. You've got to end up back where you started.
We need to get touching.
No, so
Yeah,
so if you start here, like, so that means you go back one. So get back to the start.
So,
Did you get it?
No. Are you just drawing it again?
Kind of stains.
Yeah. Let's
So,
where are we starting? Let's start at the top.
okay, done this time.
So you figured it out.
Yeah.
So let's start here. Where do we need to end up as our last choice? Either there or there. So you've got to and quarters opposite. We're aiming to end up there or there. So I reckon let's aim for this one to the end. I reckon I'm going to try and get everywhere except. So I'm going to go.
I'll try everyone in the middle.
Here.
I'll try and back
There.
there. I think there's I saw there.
I don't know if this way is going to work.
You wish you don't.
It's like getting
That's true.
there's two.
let's just go. Let's try that same start.
Yeah,
Work right there.
I want to try this one.
Got it, sir.
Transfer on the data.
I almost this one I got closer. Alright, let's get to there. You do it there. This is Rory and Clayton, you guys got one?
Yeah.
So I think I have an example of it solved on the next page. No, I don't. Yeah, well, no. Give us you have two different ones. Here's the solution. It's a bit like a G. It's very it's kind of weird because it's very mathy in what we're trying to do, but there's no like formulas or anything involved. So you must have good visual thinking. Sorry. Okay, guys, we will we won't get in the exam something like as complicated as that because that is quite a complicated one. But you will be asked: is a graph Hamiltonian or semi-Hamiltonian as well? If you want to have a look at, there's lots of different answers. Rory solved it two different ways. If you want to have a look at his sheet. So a Hamiltonian. Sorry, yeah, I'll get you to write these ones down as well, guys. Hamiltonians contain a graph called a Hamiltonian cycle. Sorry, it contains a cycle called Hamiltonian that involves every vertex, allows you to begin at any vertex, visit every vertex once, and return to the start. Semi is an open path that includes every vertex. So what you did to start with, Clayton, you know how you started at a point and you ended up at a point without reusing anything. That was actually semi-Hamiltonian. So if you don't close it, it's only semi.
Oh, you write them down.
Yeah, just those two definitions for Hamiltonian and semi-Hamiltonian, and that'll be the last writing we do today.
We can do it. I don't like two or three days now. Try doing it again like a different way. Okay.
Yeah, there is a few different ways.
Was
Hamiltonian. Yeah, so that was what was his name? William Rowan Hamilton invented this. There's a really famous problem in maths called the traveling salesman problem, where it's this idea if you send this guy to a country and he wants to like visit every town and city once, and he doesn't want to like visit a town he's already visited because that's like a waste of time because he's already visited there and sold his stuff. Can like can will it always work without him being able to visit every city? And what's the quickest way he can do it? And it sounds kind of like a simple problem, but it's actually super duper complicated. And if you can solve that problem, I think it's like a $10 million prize if you can solve it. Like no one's ever solved it. Um, um, yeah, so there's a few problems like that. They're called the Millennium problems, and if you can solve them, yeah, you wouldn't need to work another day in your life. Maybe that's what I should spend my life
Was there a
doing.
way?
Maybe we don't know. No one has figured out a way yet.
What's it called? Oh, good.
The traveling salesman problem.
How many?
Well, we're saying, can you do it every time? Like, can you prove that it's doable every time?
Traveling salesman.
So if I like sent you to Germany, can you do it for every town in Germany? If I sent you to Australia, or if I sent you to Tasmania, can you do it for every town? Yeah. Or every city, like whatever it is. And like, even though, um, even though like, that's a made up example, like going to every town, it affects other things. Like you might use that for like, if you're a trucking company, where do you send your trucks so that your drivers are doing the least amount of you know, double dipping on roads, going through places that they don't need to go through. But that's not where you guys get your pencils. Let's change the questions on page 421. Why is it probability?
I think probability is like the shittest math thing. Math concept.
Right. Thank you.
So you see the structure. So you see the answer the question.
Traveling salesman.
Yeah. How see that?
That's not how ChatGPT works, so it doesn't think for itself. I don't have a ChatGPT account. I did hear that Snapchat AI. Oh, that's right, because you can talk to it and be like, and it gives you. I saw a Yeah, I saw someone posted a screenshot and it's like proving that it's using your location data, and it was like, where's the nearest thing to me? Where's the nearest McDonald's to me? It's like, you should go to the McDonald's on the corner of the street, that street. Then he goes, how do you know my location if you're not using my location data? I was like, I do not use your location data
You can't. Yeah. Yeah. I did.
to get. Jeez, I can't say I'm worried about not having Snapchat then. Okay. Guys, once you got that down, I'll get you to have a go at question 1 and 2 on page 418. That's the Eulerian stuff. And the Hamiltonian stuff's on page 422. You may. I'll hand out this practice exam if you finish that, and you can make a start on that. But I will just jump to the next slide in a minute, just for the people that are watching the recording. I don't know, what's your bets, guys? We've got how many people away? We normally have 13 or 14 people. So if we've got 7 people away, how many views do you think I'll get on this video?
Mary.
Maybe Bronte. I wouldn't put it past Bronte to catch up at one point. Probably not immediately. Well, he's not in this class anymore. He hasn't been in this class since like term 1. No. He dropped down. I think he is. I think he's a bit slack though. 418 for Eulerian, 422 for Hamiltonian. So for those people watching at home, yep,
Are you gonna put the minutes?
sure will. So is that. Guys, I'll leave that up there. So that's a challenge. If you want to have a go at that once you finish those textbook problems. But I'll finish the recording there.